Hello everyone, this is team number 2. Our break is a design and evaluation of a baseline of the chiller for a baseline data center. Our teammates are Consuegra, Juan, Cuervo, and myself, Kamal, Alonso. Here this is an overview of our project where we're going to talk about a problem statement, the standards of a chiller, our designs, our conclusions, and final words. For a problem statement, we are going to design and evaluate and manufacture a chiller plant by providing water to a cracked unit. So for project motivation, our project motivation is to gain engineering knowledge in the HVAC field and to be part of an ongoing research project. Our project objective is going to be to design a low-cost 36-ton chiller and install it for cooling of a baseline data center and evaluate and study its performance.
The literature survey, nowadays more than ever, companies and organizations around the world depend on reliable IT operations, and therefore data centers can be considered to be the backbone of the modern economy. Due to large growth in data centers around the world, their energy consumption is accounted to be 1% in the world and 2% in the United States total energy. Nowadays, up to 50% of the energy consumption in data centers is in the US is cooled for cooling purposes. As computers get smaller and more heat and the same or more power is used, more heat is being generated in data centers. Hence, the importance for efficient cooling methods and equipment has never been greater in the IT industry. Not only to save money, but also to reduce the carbon footprint. Data centers can be water-cooled or air-cooled. Usually they are air-cooled, and in order to do this, cold air is being provided by the computer room air conditioning unit or a computer room air handling unit. In the last unit, that unit needs to work in conjunction with a chiller plant. The chiller plant is located outside of the data center, and its function is to provide constantly cold water to the computer room air handling unit. As far as the standards to be used in this project, this may be considered to be the main ones. The first one is the ASHRAE standard 90.1, which addresses the minimum energy requirements for buildings and equipment used in buildings, including chillers. ARIC standard 550/590 will address the performance ratings for water chillers, the ones that use the vapor compression cycle. ASHRAE standard 34 classifies refrigerants into 6 different groups according to their toxicity and flammability. And lastly, the ASHRAE Technical Committee 9.9 will provide different thermal guidelines that are useful for data center design.
Hello. For our first alternative, we are using a direct expansion computer room air conditioner, and it uses a vapor compression refrigeration cycle in order to provide cool air to the server racks right here, and it uses refrigerant in the cycle in order to maximize the heat absorption and the efficiency of the process. The advantages for this design are low cost compared to the other two and very efficient. The disadvantages are that it is a very unstable system when working at low temperatures, since the compressor is going to be turning on and off, and it's going to start the circulation of hot air.
For our second alternative design, we got a water-cooled chiller. This is the most expensive design. So as we can see on the diagram, we got this design have 3 different sections, which is the chiller that is composed by the refrigerant cycle, the crack unit, which is going to be inside the data room to be cooled, and we got also an outdoor section, which is the cooling tower.
The third alternative will be an air-cooled chiller. The main difference between this one and the last one is that the condenser will be air-cooled by fans, which means that we don't need to have a cooling tower, additional piping, and an additional water pump. Therefore, the initial capital investment will be lower. Now, unlike the DX crack unit, this unit will be more stable at a wide different ranges of temperatures that are going to be used to test the data center at different conditions, which is the whole purpose of Dr. Lin's research.
So we decided to make a design selection, and we made a chart in order to make a comparison between the three designs. So as we can see, the initial cost is going to be better on the degas crack and the air-cooled chiller. That's why we're not using a water-cooled chiller design. In efficiency, all the three chillers are going to be very efficient in the market, but the capacity changes in the water-cooled chiller. So, but as Victor said, the stability of the DX crack is not very good, since when the cooling loads are very low, the compressor is going to be turning on and off, and that's going to be a problem. So we're going to go with the air-cooled chiller as our final design.
So as I already mentioned, the final conceptual design will be an air-cooled chiller based on some preliminary research for different catalogs from manufacturers and ongoing calculations. We have determined that the condenser will be an air-cooled condenser, the compressor will be an scroll-type compressor. You will have an thermal expansion valve, and the evaporator can be either a braze-made evaporator or a DX shielding tube evaporator. Also, the pump will be a centrifugal pump, and one of the most important components will be the refrigerant. So for the environmental impact this project may have, we're only taking into account refrigerants that are approved for HVAC applications. Right now we're considering 3 different refrigerants. There will be the R134A, the R47C, and the R410A.
Okay, this is our timeline, which can be seen here, and we are right here now. We got this part to work on, and we want to be done by the end of the year, December. This is the chart of responsibilities, and here we can see how the responsibilities and the topics were distributed between the teammates, and a lot of teamwork was done also, by the way. For our perspective for global design, we want to provide user manual in English and Spanish, also as well technical manuals in both international systemic units and English units, and develop data center standards depending on the outcome of the research, which is funded by Azure. And we want to implement these standards in the United States and eventually all over the world. So for conclusion for this project, we wanted to select a cooled chiller, and because of the low cost and stability issues and cost, we are going to select this one. And also market availability is very important, because we can find the components and everything else to build it very easily. And for the desired maximum heat capacity, this one is also the best one. Future work, we are gonna do some temperature analysis, simulation, optimization of the system, as well as we see the results. Then manufacturing, validation and testing, and then propose our final design, manufacturing. Any questions?
Okay, low cost. How low is low? How do you define low cost?
For an air-cooled chiller right now in the market, that will be $45,000 for a 40-ton capacity. The one we need is a 36-ton capacity, and that's one of the motives to do this design, because we can actually.
So how much lower than?
Well, we're expecting to have it lower than 30,000.
So less than 30K.
Less than
Okay.
30.
Second question I have for you is, you made a statement that you're going to reduce the carbon footprint. How are you going to do that with this system?
I'm sorry.
Well, I didn't say we are gonna reduce the carbon footprint. What I said is that since data centers are increasing its generation, one of the problems is that these industries are polluting a lot of the environment. So one of the reasons why this industry needs a standard is to actually increase the efficiency in their design, data center design. But this is going to be only to cool down the data center. The baseline data center will be designed by Dr. Lin and his PhD students, and the whole purpose is to create these standards.
Because I think you've got an opportunity here. You've got an energy source that's generating heat on the system. You're actually spending energy to cool it, but you're not using the energy that you're getting from the system to basically run it or to be a benefit and basically reduce the carbon profile. So that's a suggestion, is to think about, is there any way to recover any of this energy and use that in your design?
Thank you.
Thank you.
Okay, and then I think the last question I wanted to ask is, when you were doing design selection, why didn't you put operating costs in your model? Because initial costs, the capitalization costs is, we can do a net present value analysis and figure out how long it costs to pay for itself, but we really have to understand how expensive it is to run the system. And is the system that you selected the most efficient on operating costs? Because over the life of the system, that may end up being a more important variable than the initial expenditure.
Yeah, that's right, actually. But that will be right for real data centers that are going to be operating 24/7. This one is only going to be used for research. This is not the data center will not be operating for 24/7.
Okay, so that my suggestion is add operating costs to
Yeah,
your
that's
your study. Thank you.
Thanks.
Why a scroll compressor?
Sorry?
Why a scroll type compressor? In your presentation, you mentioned that
Yeah.
you chose that type of compressor.
The
Why?
scroll type? Okay.
Yeah.
There are basically 4 types of compressors that these type of chillers use. There are reciprocating type, scroll type, and water-cooled compressors use screw type and centrifugal types. The water-cooled chiller will be oversized for this kind of application, since we only need 36 tons. So the reciprocating type will be the capacity will be so low that will not be able to handle 36 tons. And that's why we use the scroll type. And if you look at the market, all of the different air-cooled chillers, they use that type of compressor.
Are you picking a one that's efficient?
Uh,
Or are you taking efficiency into the equation?
That will be part of the equation, but the most important thing for us will be to reduce the cost.
Okay.
Very expensive system.
What happens if you don't reduce the cost?
I'm sorry, sir?
What happens if you don't reduce the cost? You consider your project a success or a failure?
It will be a failure, because that's the main goal.
Any other comments from advisory board members, from visitors, guests? Thank you.